Okay, so let me tell you what I'm doing. I don't know if it's going to work or not, but I figured. One of the things I realized is that these are very long lectures. And when I post a video, you're talking about a video about an hour and a half long. It's kind of like a lot. So what I'm trying to do tonight is to kind of like break it into pieces. So for example, when we do when you look at the recordings in Canvas, that portion that we just did right now is going to be one video. And then this next section is going to be a separate video. So we'll see how that works. Again, I'm open to feedback. If you guys think it's, waste of time or on my part or whatever, that's fine. Okay, cool. Okay, so let's talk about something interesting. The important thing about these solubility equilibria is that they allow us to have several applications of it. And we're going to start with the first of them. And the first application we're going to discuss is, can I predict how something is going to be, let's say, precipitating, if something is going to precipitate or not, all right? So this is our first application. I'm going to see if I can predict whether a precipitation reaction will happen or not. All right. Okay. So here's the problem. 2.00 milliliters of 0.200 molar NaOH are added to 1 liter of 0.100 molar calcium chloride. Will a precipitate form? And they give me some KSP value here, but I got to find out what it is for. Okay. It's kind of like KSP is 4.7 times 10 to the minus 6. KSP of what? Okay, well, let's build our case here. Number one, what are the ions that would be present in this mixture? Okay, we have sodium hydroxide, calcium, and chloride ions. Not in a 1-to-1 ratio, because remember the chloride ions, there's 2 of them for every calcium. So I'm not saying these are the ratios, just which ones are present. Now the question is, what combination of ions here would give me a potential precipitate? So the options are sodium hydroxide, calcium chloride, which you already have, sodium chloride, calcium hydroxide. So this is where you had to pull out your solubility table. If you don't have one with you, or you don't want to carry around that slide that I showed you a few slides ago at the beginning of the lecture, you can go to chapter 4 of Top Hat, and they have this chart. It's a little different the way the other ones are, but you can look in here on the top, soluble compounds, on the bottom, insoluble. So let's see if we can find out the hydroxide. It says here, hydroxides are insoluble. What are the exceptions? 1A cations, ammonium, calcium, barium, strontium. So those guys over there in the bottom, those are slightly soluble. So we're going to say, well, maybe the only one that I can think of here, in other words, if the cation is group 1A, it's an exception. So that would be sodium hydroxide. That wouldn't work out. So let's try out calcium hydroxide here. All right. So let's go ahead and go here. All right. Let me get those markings out of the way. All right. And let's come back here. So the candidate that we have is calcium hydroxide. That's the one that could form, that might be sufficiently insoluble that it might form a precipitate. All right. So that means probably that KSP that they gave us was actually for this compound, right? So the question now is the ion product larger than KSP? Remember, if the ion product is less than KSP, the solution is unsaturated. There is no precipitate. If Q equals KSP, then the solution is saturated, which means you are at the maximum possibility of solubility, and therefore there's no precipitate. So the only way you get a precipitate is you're generating a mixture here that has an ion product greater than KSP. All right. And we said that KSP is 4.7 times 10 to the negative 6. So what we need to find out is what are the molarities of these guys. All right. So what is the molarity of the calcium? Well, one thing we're going to do here is you have 1 liter of solution of calcium chloride, and you are adding 2 milliliters. That is not a sufficiently significant dilution. So for all practical purposes, we can assume that the calcium ions are staying at 0.100 molar. Now, for the hydroxide ion, doesn't work that way. We have to use our good friend, the dilution formula, right? So we had to calculate the hydroxide ion concentration here, right? So that should be 2 milliliters of 0.2, right? Okay, this is the part of the screen where my thing doesn't work very well. 2 mLs. I ran out of space here. Okay, you guys know how to do this, right? Sorry about that. I ran out of space. Anyway, you have to dilute the hydroxide. 2 milliliters of 0.2 diluted into 1 liter will give you essentially, it's essentially a 1 in 500 dilution. So you're going to get 4 times 10 to the minus 4 molar, right? All right. So now we're going to calculate the ion product. Careful. Don't forget that we have here a squared value. So 0.1 molar times the square of 4 times 10 to the negative 4. And that gives us 1.6 times 10 to the negative 8. So KSP is 4.7 times 10 to the negative 6. Ion product is 1.6 times 10 to the negative 8. In other words, the ion product is less than KSP, which means this is going to be an unsaturated solution, and therefore no precipitate will form. All right. Leave it there for a few more seconds. Let me know if there's any questions. Okay, cool. Okay, so that's application number 1. It's predicting whether a combination of solutions will give us a precipitate or not. Remember that when we do these precipitations for qualitative analysis, we pretty much overload our solutions. We make it to where if a precipitate can form, it will form. We typically put excess of our precipitating agents. But you can see where you can manipulate conditions to limit the amount of precipitating agent. Now, for example, we discussed when we were doing the group 2 cations, we said the reason why those ions precipitate at a low pH is because you are producing a lot less sulfide ions and therefore causing these guys to precipitate, whereas the group 3 ones don't precipitate at that concentration of sulfide ions. So you can see how you can manipulate concentrations so that you will selectively precipitate something but not something else. Speaking of which, let's go and look at another problem here. This is what we would call fractional precipitation. So here's the question. What concentration of silver ions is required to precipitate only silver bromide in a solution that contains both bromide and chloride at a concentration of 0.020 molar? In other words, you have a solution that has, let's say, for example, sodium bromide and sodium chloride dissolved, and the concentration is 0.020 molar. And I am going to start adding silver ions, probably in the form of silver nitrate or something like that. I'm going to start adding them. And I know that both silver chloride and silver bromide will precipitate. And chloride and bromide ions are part of group 1, right? Actually, it's a different I'm sorry, my bad. Sorry. Silver is group 1 and therefore it precipitates with chlorides, but it also precipitates with bromide ions. All right. So what we're going to do is let's write out each one of these. Now, I wish they had given us the values of KSP, but we're going to have to look it up. But here's our first one. Silver bromide in equilibrium with silver and bromide ions. Again, we have to look up KSP in that chart, in that table, either in Top Hat or wherever. And the KSP for this equilibrium is 5.4 times 10 to the minus 13. Now, notice, this is a different kind of problem. All right, I'm not being asked to calculate what is the molar solubility. I'm asking, at what concentration of silver can I precipitate just silver bromide, but not silver chloride? So let's deconstruct KSP, which is the product of the two concentrations. And let's say, what would be the concentration of silver that generates values corresponding to KSP? So I'm going to rearrange this equation. KSP divided by the bromide ion concentration. And KSP is 5.4 times 10 to the minus 13. The bromide ion concentration is 0.020 molar. So when I calculate that, I get 2.7 times 10 to the negative 11 molar. Okay, what does that number mean? Well, that number means that at that concentration of silver ions, you are going to be in saturation levels. In other words, that is the concentration of silver ions that will multiply times 0.02 to give me KSP, which is the equilibrium constant at saturation. Okay? Now, the question was, how can I make sure that I'm not precipitating the chloride ions? In other words, the silver chloride. Well, let's see what kind of concentration of silver ions does it take. Same analysis again. I have silver chloride dissociating into dissolved silver and chloride ions. I had to look up the value of KSP, 1.8 times 10 to the negative 10. I had to deconstruct it into the product of the two ion concentrations. And now, just like I did in the previous set here, I'm going to find out what is the silver ion concentration when the system would be saturated. All right, so that'd be KSP divided by the chloride ion concentration. So the chloride ion concentration is also 0.020 molar, but the KSP is a different number. And that gives us 9.0 times 10 to the negative 9 molar. So notice that this concentration is, roughly about, I don't know, 400 times more concentrated, right? In other words, somewhere between 2.7 times 10 to the negative 11 and 9 times 10 to the minus 9 molar. That is the molarity of silver ions you want to put in here. In other words, if you put less than 2.7 times 10 to the negative 11 molar, nothing's going to precipitate. If you get to 9 times 10 to the negative 9 molar or above, both compounds are going to precipitate. So you want to find somewhere in between there where you calculate how much of the silver ion should I add in between those two values, and that way you'll be able to precipitate only silver bromide, but not the silver chloride. All right. Okay. Well, let's do this. I think I went over a little bit here. So let's take a little 10-minute break. All right. And then we'll come back and we'll be able to continue this discussion. So if you have any questions, you can post them during our break here in our chat room. Okay. All right. So we're going to pause the recording here for a moment and take a 10-minute break. All right, we are back. So we have another interesting exercise to work on here. And that's on the next slide here. All right. I'm not sure if this is actually going to be in your set, but just in case, this is the one you just did right now. Let's go through it. Oh, I forgot to show the precipitates, but I skipped it because I don't think you can tell the difference between them. The silver bromide is a little kind of beige. Silver chloride is white, but I don't think you can tell here in this picture here. So anyway, here is another example of how to do fractional precipitations. If you add solid silver nitrate slowly to a solution that has 0.100 molar each in sodium bromide, sodium chromate, sodium sulfate, in what order will the silver compounds precipitate? So kind of like, you've got to kind of like read between the lines here, right? You got to kind of like get a sense of, okay, what's going on here? So I have a solution of these three compounds. All three of them should be soluble, perfectly soluble. But when I add silver nitrate, the silver bromide, the silver chromate, the silver sulfate compounds that could form from the exchange of ions are insoluble. So the question is, since we're adding the silver nitrate very slowly, essentially you're asking is which of these compounds will precipitate as at the smallest possible molarity. Okay, so let's go to our makeshift whiteboard here. I'm going to come over here, and here is the same slide we just did. All right. So again, first thing we do is we've got to write out the appropriate equilibria. So I'm going to write them just in the order that they are in here. All right. So the first candidate here would be silver ions combining with bromide ions to give me silver bromide. And when I calculate that, I get silver and I get bromide ions. And I'm going to have to look up what is the KSP of that. So again, it's one of those problems where they didn't give you the KSPs, but hopefully they'll give them to you if you have this in a test, right? 5.4 times 10 to the minus 13. And this is very similar to the previous example. You're asking, at what concentration of silver ions will this system be in equilibrium? In other words, at what concentration will this system be saturated, all right? So remember that KSP would be equal to the silver ion molarity times the bromide molarity. So the concentration of silver ions at saturation will be KSP divided by bromide. So that's 5.4 times 10 to the minus 3 divided by 0.100 molar. Oops, sorry, minus 13, I'm sorry, not minus 3, sorry. And that would be 5.4 times 10 to the minus 12 molar. All right, so that means that if I'm adding silver nitrate slowly, when the silver ion concentration reaches that level, I'm going to start precipitating silver bromide because that's kind of like the maximum, that's the saturation level. Okay, everybody understand that? Cool. All right. So let's try the other one then. The other candidate would be the silver chromate. Now, chromate is a -2 anion. So that means that we have this here. All right, so we have to adjust for that. That means that when you dissociate those ions, be very careful. There are 2 silver ions in here for every chromate ion, or for every unit of the compound that dissolves. All right, so KSP here is silver ion squared times chromate ion. Oops, I forgot this is 2 negative. And we had to look that one up. Let's see what I have here. I have 1.1 times 10 to the negative 12 as the value of KSP. So that means that here, the silver ion concentration I'm looking for would be KSP divided by the chromate ion concentration, but I got to take the square root of that because this is going to be squared in here, right? Square root of 1.1 times 10 to the negative 12 divided by 0.100 molar. Remember, they're all 0.100 molar. And it looks like we get here 3.3 times 10 to the negative 6 molar. So in other words, around that concentration of silver ions, the silver chromate will begin to precipitate. Notice that that is several orders of magnitude larger than the molarity at which silver bromide was precipitating. So it's going to be a while between them, but we have one more guy here, and that is the sodium sulfate. All right. So when silver meets sulfate, it will form a silver sulfate precipitate. And once more, careful with the stoichiometry, that's 2 silver ions per unit, and then 1 sulfate ion per unit. So notice that one of the things that happened here is you had to kind of like either intuitively or just looking it up, figure out, what are the things that could precipitate here, which means I got to have that solubility rules table handy just to make sure I know what I'm dealing with. So this is very similar to the previous one, right? So KSP here would be equal to the molarity of silver squared times the molarity of sulfate. And I think the value for this is 1.4 times 10 to the negative 5. Again, that's a value that I looked up, all right? So like I said, several things you may have to have handy. Your solubility chart, your KSP chart. We have those in your Top Hat book in different portions. Okay, so in this case, the molarity of silver at which this compound will be at saturation will be the square root of KSP over the molarity of sulfate ions. So that's square root of 1.4 times 10 to the negative 5 divided by 0.100 molar. And I think that comes up to be 1.2 times 10 to the negative 2 molar. So notice that all these calculations are very much a repeat of the previous example we did. We're just trying to ask ourselves at what concentration of the challenging or precipitating reagent are we getting an actual precipitate of this particular compound, all right? So for silver bromide, we had 5.4 times 10 to the negative 12. For silver chromate, we had 3.3 times 10 to the minus 6 molar. And for silver sulfate, we had 1.2 times 10 to the negative 2 molar. So in other words, the order in which they will precipitate is first silver bromide, because it'll precipitate at a very, very small concentration. Followed by the silver chromate, right? We can put this solid here because it precipitates, at about 3.3 times 10 to the negative 6. And then it'll be a while before the silver sulfate will begin to precipitate when the silver ion concentration reaches 1.2 times 10 to the minus 2 molar. All right. Okay, let me get you guys kind of like absorb that. But I'm going to ask a question. And the question is, couldn't we just use KSP to answer this? I mean, look at this. Who has the smallest KSP? Silver bromide, 5.4 times 10 to the minus 13, followed by silver chromate, 1.2 times 10 to the minus 12, followed by silver sulfate, 1.4 times 10 to the minus 5. So why couldn't we just simply use KSP to make the prediction? Why have to go through all these calculations? I'm pretty sure you had the same question, right? I'm pretty sure you did. All right, so let's see if we can deal with that question now. I'm gonna bring another copy of this thing here. Okay. So the question we're asking is KSP value sufficient? Well, let me give you an example. Let's say that you had also had, assume that you also had let's say sodium phosphate in the solution. In other words, I'm going to be producing silver phosphate, but silver phosphate is Ag3, right? Which gives me 3 units of silver ions for every unit of the trivalent phosphate ion. So the KSP of this would be the silver ion concentration cubed, right, times the phosphate ion concentration. And this KSP value, if you look it up, is 1.8 times 10 to the minus 18. It's very, very small. The question we're asking is it enough to base it off of the KSP? So if that were the case, you would say that this is very small. So you would say, well, would it precipitate before the silver bromide? Remember, in our initial step here, we said that silver bromide has a KSP of 5.4 times 10 to the minus 13. So we would think, well, since that is so much smaller here, shouldn't it precipitate first? Well, let's see. The silver ion concentration that I need to precipitate silver phosphate would be the cubic root of KSP over the molarity of the phosphate, right? So that would be the cubic root of 1.8 times 10 to the minus 18 divided by, let's assume that it was the same molarity as the other guys that we had in there, 0.100 molar, right? Okay, guys, I don't know if your calculator has cubic roots or something like that. I think mine does, but like I said, I can't find it. I'm going to look it up when we go to our next section, hopefully. But here's the thing. You can probably work it out anyway. So it turns out that the molarity here that we require is actually 2.6 times 10 to the minus 6 molar. In other words, it's kind of in the range of the silver chromate. Therefore, silver bromide precipitates first. And therefore, KSP value is not enough. It's not sufficient. Well, let's see, KSP value alone is not enough to predict the order of precipitation. All right. So there you have it, ladies and gentlemen. Major application of solubility equilibria is our ability to distinguish how things are going to precipitate. If I have a mixture, who's going to precipitate first, or at what molarity can I precipitate one but not the other one? So very interesting problem here. All right. So let's come back over here and let me see if there's any questions. Don't forget, I'm going to scan these things and they'll be posted. All these notes will be posted for you along with your recording. All right. Let me know if there are any questions. All right. Okay. Let's